This is 6.1.1, circular motion. Now the first thing we're going to do is we're going to introduce a new quantity called the angular frequency, or sometimes we call also the angular velocity. So imagine something's moving in a circle and we take a look at a portion of its motion moving in a circle. So if it starts here and moves around up to about here, and this is the end, then it would have had some linear velocity which will be tangential to the circumference of the circle that it's tracing out as it moves in a circle. And because it's moving in a circle, that means there must be a radius. So that's r, the radius. And as it moves in a circle, it moves by some angle, theta. So we go back to basic mechanics and we define velocity. So from AS physics, velocity is defined as the rate of change of displacement. Angular velocity, or angular frequency, is the rate of change of angle. So angular velocity, and we denote that with the symbol lowercase omega, which looks like a curly W, measured in radians per second. Is the rate of change of angle. Now, just like in mechanics, you're going to have to memorize some equations. So we're going to give you the basic ones. So if you know the arbitrary angle that this thing is moved in and the time that it's taken, then we can work out the angular velocity. So omega is equal to theta over t. Or you know how many revolutions it does per second, or you know how many seconds or how many minutes or the time it takes to do one revolution. So if we think about circles, to do one whole revolution, so one circle, the angle is 2 pi radians, which is 360 degrees. And the time taken for one full circle is called the period, because if it keeps moving in a circle, it's periodic motion, like a wave almost. So it has a period. So if you know the time taken, or the period for one full circle, then we can do omega is equal to 2 pi over capital T, which is the period. Now notice those two equations are basically the same thing. Now, if you know the period of something, you also know its frequency, because frequency is 1 over period. So 1 over period, you got 2 pi over t. So yet another form of that is 2 pi f. And then the last one, which is the only one that looks different to these, but eventually when you start using all the equations, you're going to actually find that they're all the same thing, is omega is equal to v divided by r. And we put a box around these. We'll define these quickly. So we've got omega, which is angular velocity, measured in radians per second. We've got theta, which is angle, measured in radians. We've got t, which is time measured in seconds. We've got capital T, which is period, measured in seconds also. We've got F, which is frequency, which is measured in hertz. And then we've got V, which is linear velocity, which is measured in meters per second. And then we've got R, which is the radius, measured in meters. Now, before I move on, I want you to imagine an object moving in a circle. It moves in a circle at constant speed. Is this object accelerating or not? And the answer to it is yes, it is accelerating. So I said it's moving in a constant speed in a circle, but it has a velocity. Now, velocity is a vector, so it has magnitude and direction. If I said constant speed, all that means is that the magnitude of velocity is constant, but its direction is constantly changing. So for the direction to change, that means velocity is changing in some way, and acceleration is the rate of change of velocity. So for something to move in a circle at constant speed or not, it is accelerating. So we're going to move on to centripetal force and acceleration. So we'll start by writing that down. An object performing circular motion is accelerating because velocity is a vector and direction is changing. So we can do that quickly with a quick sketch. So here's a circle. Here's an object doing circular motion. So at each point, 1 to 4, the direction of V is different, which means that it's changing. Now, if there is an acceleration, there must be a resultant force, because F equals ma. So if the thing is accelerating, then it also must have a resultant force. So if object is accelerating, there must be a resultant force. And we call this resultant force that causes things to move in a circle the centripetal force. So, I'm going to write the equations out, which you need to learn. And I'm going to write them spaced out on purpose so that we can see how they relate to F equals ma. Because all of these equations are just F equals ma, but in a different form. So the first one is F equals to m r omega squared. So F is in the same place. M is in the same place, but in addition we've got r omega squared. So F equals to mr omega squared. So r omega squared is our centripetal acceleration. And another form of this is F equals to m times v squared over r. So in that bottom form, v squared over r is our centripetal acceleration. Put a box around that. So far, you've had to learn 4 equations for angular velocity. Omega equals to theta over t, omega equals to 2 pi over t, omega equals to 2 pi f, omega equals to v over r, and then 2 equations for centripetal force, F equals to mr omega squared, F equals to mv squared over r. So 6 equations in total for today's lesson. And next you have to consider how different objects actually move in a circle. So let's look at a few different examples. Start a new page. So this one is a bridge. So this bridge is kind of like a half circle, or it might even be less than half circle, but nevertheless it's circular shaped in some form. And therefore it has a radius of curvature, which is r. So if you imagine that sort of trace out a larger circle. Now this object is moving to the right. So its velocity is to the right. Now, we want to consider the forces acting on this object that will make it perform circular motion while it's on this bridge. So for it to perform circular motion, its velocity is going to curve downwards in the next instance. Now, as it's moving forward, we're going to see that some things happen that you might not expect when things are stationary. So let's assume first it's stationary. If that was stationary, there are 2 forces acting on the object. Its weight pointing down, and then the normal reaction from the bridge on the object pushing up in equal magnitude. So the resultant force would be 0. But if the moment that starts to move, or that has already been moving, in the tiniest of instants, the bridge is curving down. So its normal reaction on the object is actually going to be less than the weight in that instance. So when I draw these forces, I'm going to draw the weight pointing down, which is rather large, and a small normal reaction. So if doing circular motion in this instance, mg is greater than r. So if we want to look at the resultant force is going to be F is equal to mg minus r. And then we can equate that to mr omega squared or mv squared over r. So therefore, mg minus r equals to mr omega squared, or mg minus r equals to mv squared over r. Now, that's if it's at the highest point. If it's not at the highest point, then because the bridge will have to cause the object to move upwards along the circle at the beginning, in that instance where the road is curving upwards, then the normal reaction will actually be greater than mg, and that will cause it to move upwards. So whenever you're looking at trying to figure out the centripetal force, you have to take that into account. There's all the forces acting. And sometimes things change. Now, if you go too fast over a bridge, then the moment you're at the top of the bridge, the next instance your normal reaction will be even less. Yeah? Because the rate at which you're moving forward is so great that the bridge can't catch up with how much force it's putting back up onto you. If you go very, very fast over a bridge, at some point you'll be going so fast that you'll take off and lose contact with the bridge. So we want to find at which velocity that happens. So we'll make a note here. As the road curves down, r is less than mg. The bigger the linear velocity is, the less r would be. And we can see that from the equation as well. So if you rearrange all of this to get r is equal to something in the form of, in relation to v, then we would get mg minus mv squared over r equals to big R. Now m's a constant, the mass of the object's not changing, the radius is not changing, g's not changing, so the only two things in there that can change is v and r. And because you've got v being taken away, if v gets larger, then big R will have to become less. So going faster makes R decrease when r becomes 0, you have lost contact with the road. You are now no longer attached to that road. Your normal reaction is 0 because there's no contact, and you take off like a projectile. So at takeoff, you've got mg minus r, but r's become 0. So mg is equal to v squared over r. So g equals to v squared over r. So the takeoff velocity then we can find by rearranging this. V equals to square root of r times g. And we notice something, the takeoff velocity does not depend on mass. So it doesn't matter what mass the object is, it will all take off at the same velocity. Okay, let's start a new page. We'll do another example, which is round the loop. So we'll do a little sketch of a roller coaster ride. And we have 4 possible positions where we can have an interest, which is the bottom, the top, and the 2 sides. Now, in terms of the 2 sides, it's a symmetric problem, so we only really care about one side, because the other side is going to be exactly the same but mirrored. So our points of interest are at the bottom here, on the side, and at the top. If we're moving in a circle, so if moving in a circle, then we have centripetal force. And centripetal force means it points towards the center of the circle. So in each case, the resultant force must point towards the center of the circle. Yeah? So let's look at the bottom. At the bottom, we have 2 forces, mg pointing down and normal reaction pointing up. But our track is curving upwards at that point. So actually, because the track is curving upwards, it puts a larger normal reaction than mg. So in that case, r is larger than mg. So when we draw our arrows, we're going to draw r bigger than mg. Now, when we're on the side, mg is acting in a completely different axis than the centripetal force. Because the centripetal force must be towards the center, which means on the side is completely horizontal. So on the side, we only depend on the normal reaction from the track. Now, when we're at the top, we've got mg trying to pull us down, but the track is also curving. So the track is also pushing us down with a normal reaction, because we haven't lost contact with the track when we're at the top. We're still touching the track. So both of them put a force on us. So we've got two forces pointing downwards when we're at the top. So we've got mg and we've got r. So now we're going to write expressions for each of these. So we'll do the top, the middle, and the bottom. So at the top, we've got r plus mg, or mg plus r, whichever order you want to put it in, equals to the centripetal force, which is mv squared over r. In the middle, it's just r equals to mv squared over r. And at the bottom, it's going to be r minus mg equals to mv squared over r. So these are our three expressions. Now clearly, again, in this situation, whether you successfully go around the loop or not is going to depend on how fast you're going. So let's say we're not going fast enough, and we reach the top and we fall. If we fall, it means we're not touching the track anymore at the top. So we've lost contact. If we've lost contact, we've lost our normal reaction. So at that point, normal reaction becomes 0. So if we fall, contact with track is lost. Therefore, R goes to 0. And if R goes to 0, then we've got mg equals to mv squared over r. The m's cancel out, and you get the exact same expression again. G equals to v squared over r. Now in this case though, we're moving on the inside of a circle rather than the outside. So we don't want lower velocity in order to do circular motion, not take off. In this case, we want a greater velocity to not fall. So we rearrange this to get v equals to the square root of rg. This is the minimum velocity to not fall. And again, it does not depend on mass, much in the same as the other one. Now, that's the minimum velocity to not fall, but there's also a minimum velocity to reach the top. Because you might only go fast enough that you get about halfway up and you don't actually manage to reach the top. So to reach the top, consider energy changes. So in this case, you've got kinetic energy at the bottom, turning into potential energy at the top. If you've gone from the bottom of a circle to the top of the circle, your change in height is 2 times the radius of that circle. So we've got a half mv squared equals to mg delta h. Now delta h is 2r for circle. So we've got the m's cancel out. So we've got a half v squared equals to 2gr. We rearrange this. And we get v equals to the square root of 4gr. So that's the velocity you need to reach the top. Now if we compare that to what we had above, you can see that it's v equals to rg, v equals to root 4rg. So this is 2 times bigger than that value we had up there, because square root of 4, that's 2. So it's 2 times root rg. So it's 2 times bigger than the minimum velocity not to fall down in order to reach the top. But along the way, that roller coaster might slow down as it tries to get to the top. So that's the amount of velocity you need to reach the top in the first place, to be able to reach the top. And when you're at the top, if you're less than half of that, then you're going to fall down. Now sometimes you might not know the radius of the circle, but you might have been given the height that you've changed by, so it's important to recognize that as well. So it could also be written as v equals to square root of 2g delta h, which is the same thing. And that's the end of lesson 1 of 6.1.1.